Here we have the last section of Chapter 5, Unconditional Probability and Independence. So we're going to be looking at calculating and interpreting conditional probabilities using the general multiplication rule, using tree diagrams, and determining if two events are independent, and use the multiplication rule for independence events and compute their probabilities. So what is conditional probability? The probability we assign to an event can change if we know that some other event has occurred. This idea is the key to many applications of probability. When we are trying to find the probability that one event will happen under the condition that some other event is already known to happen, then we're trying to do a conditional probability. The probability that one event happens given that another event is already known, again, that is called a conditional probability. So suppose that we know that event A has happened, then the probability that event B happens, given that event A has already happened, is denoted by P of B. This vertical line is given A. So this would be read as probability of B given A. To find the probability of A given B, we find the probability of A and B and divide by the probability of B. Likewise, we can switch that around, find the probability of B and A, that's the intersection up here, and we divide by the probability of A. So notice the way that we write this, whichever one is given is the one that we're dividing by on the bottom here. Okay, so now looking at a two-way table where we have students at the University of New Harmony, we have 10,000 course grades from last semester. The two-way table breaks down these grades by which school the university taught the course. So we have liberal arts, engineering, and physical sciences, and health and human services. So those are the three colleges. We have college grades tend to be lower in engineering and physical sciences rather than liberal arts and social sciences. Choose a University of New Harmony course grade at random. Consider the event E is that it comes from the School of Engineering and Physical Sciences, and L means the grade is lower than a B. Find the probability of L. So L, meaning lower than a B, what we want to do is look at all of the grades that are lower than a B, which is here. Probability of L is and then we divide that by the total, which is 10,000. So as a decimal, we would say that is 0.3656. Interpret this probability in context. So remember, we don't say that there's a 36% chance that someone has a grade lower than a B. We say if we select many or a large number of students in this university, we expect 36.56% of them to earn lower than a B. Okay, now we need to find the probability of E given L and the probability of L given E. So when we have a two-way table like this, so the formula from the previous page is certainly an option, but when we have a two-way table like this, I like being able to, if we're given L, where L is being lower than a B, then we want to find where E and L intersect, which is here. So we have engineering and L, which is lower than a B. We have where that intersects, and then we divide by the total of whatever the condition is. So this is under the condition that we've earned lower. I'll move this a little bit. We've earned lower than a B. So then we divide by that number, 3656, which is about 0.2188. And then similarly, we're going to do the other direction, the probability of L given E. So we still use 800 because that's where the L and the E intersect, but we divide by the other total. This time we're dividing by the total of engineering and physical sciences. 1600 or 0.5. Which one of these conditional probabilities tells you whether the college's EPS students tend to earn lower grades than students in liberal arts and social sciences? So because this second one that we just calculated, this guy, because that is divided by the total, only looking at EPS students, this tells us that EPS students are more likely to earn lower grades than liberal arts and social sciences, because 50% of engineering students get lower than a B, whereas only 21.88% of engineering students are, given that they earn lower than a B, are engineering students. So this one for sure, the second one tells us that engineering students earn lower grades. To be fair, as a math teacher, I can attest to the fact that those classes are just straight harder. Okay, so now to find the probability of A and B, there is a specific rule called the general multiplication rule. If we don't have something like a two-way table. To find the probability of A and B, we find the probability of A and multiply it by the probability of B, given A has already happened. Oops. In other words, this rule says for both events to occur, first one of them must occur, and then the other, given the first has occurred, must occur. So one way of dealing with this is tree diagrams. The general multiplication rule is especially useful when a chance process involves a sequence of outcomes. In such cases, we can use a tree diagram to display the sample space. So here we are flipping a coin twice. Over here, we just toss the first coin, and there's two outcomes, right? We have heads or tails, and on each of those little lines, we put the probability of each. And then after the first toss, we have heads and tails. After the second toss, we have heads and tails. So to find the probability of getting two heads, we follow the path of first head, second head, and we multiply the two probabilities. 1/2, 1/2, and that's how we get to 1/4. So looking at another example similar, we have the Pew Internet and American Life project finds that 93% of teenagers use the internet and 55% of online teens have posted a profile to social networking sites. What percent of teens are online and have posted a profile? So here with our tree, first we have a teenager. And our first question is, are you online? Yes or no? If yes, 93%, no, 7%. If you're online, do you have an online social networking profile? Yes or no? So it says 55% of those online have a profile, so 45% don't. And then, of course, over here, if you don't have an online presence, you certainly don't have an online profile. And to find the probability of yes, online, yes, a profile, you follow that specific branch. And probability of online and profile. In this case, we care about the probability of a profile, and we have to do, hold on just a second. Yeah, probability of profile has to be given We're online because obviously those that are not online don't have a profile, so the online has to be the given. So we do probability of online times the probability, whoops, we don't want to put equals here. I was saying that we need both of these things. This is 0.55, and the probability of online is 0.93. I think I'm going to move this so it's not quite so. I guess erase it and try again. Probability of online and profile, oops, that's up there, equals probability of online times probability of profile given online. Okay, so now we piece all these things together. Probability of online is 0.93. Probability of profile given online is 0.55. You don't have to write this quite so officially. If you have a tree, you can just do 0.93 times 0.55, and we get 0.5115. So our summary here is 51.15% of teens are online and have posted a profile. All right, let's do an example where we don't already have a tree set up for us. So we have a computer company that makes desktop and laptop computers at factories in 3 states, California, Texas, and New York. California factory produces 40% of the company's computers, the Texas factory makes 25%, and the remaining 35% are manufactured in New York. Of the computers made in California, 75% are laptops. Of those in Texas and New York, 70% and 50% respectively are laptops. All computers are first shipped to a distribution center in Missouri before being sent out to stores. Suppose we select a computer at random from the distribution center. Construct a tree diagram to represent the situation. It's going to be a little tight here. I think I'm going to make a new tab to set this up so we have just computers in general. To the 3 locations, California, Texas, New York. California had 40% of the computers in general, Texas had 25%, and New York had 35%. In California, they said that 75% of the computers were laptops. LT for laptop, we'll do DT for desktop. If 75% are laptop, then 25% are desktop. Makes sense. In Texas, they said 70% were laptops, which means 30% were desktops. And in New York, 50-50 laptops and desktops. So there's our tree diagram. Second part of the question said, find the probability that the computer is a laptop. Show your work. So if I'm looking at this next, at the tree, I want to look at the end goal here. Laptop, laptop, laptop. So how do I end up at the end of all 3 of those branches? So what I have to do is multiply the California laptop branch, the Texas laptop branch, and the New York laptop branch. Write this down. So we have the probability of a laptop in general. Whoops. Laptop is the 0.4 times 0.75, California, plus 0.25 and 0.7, Texas, and 0.35 and 0.5, which was New York. Multiply all three of those together, and we get 0.65. So the probability, whoops, wrong way, probability of choosing a laptop in general was 0.65. Given a laptop is selected, what is the probability it was made in California? So this is part B, part C. Given laptop, what's the probability it was made in California? So remember that we do a probability of A and B, so California and laptop, divided by the given probability, which in this case is laptop. Probability of California and laptop is shown here in our work, 0.4 times 0.75, and divide by the probability of having a laptop in general, 0.65, which is what we just found in part B, and we divide that, get 0.462. Okay, now let's talk about independence. When knowledge of one event, that it has happened, and it doesn't change the likelihood of another event happening, we say that those two events are independent. So if the occurrence of one event does not change the probability of the other event. So these are how we can check this with, this is not a very good job, I'm going to highlight. Here are two probabilities to check independence. If the probability of A given B is the same thing as the probability of A, or the probability of B given A is the same thing as the probability of B, then we know that A and B are independent. In general, we can just stick with one of those two things. So if we know we have independence, so remember that the other rule was the for AND was the probability of A and B is equal to the probability of you find A and do the probability of A and then the probability of B given A. But if we know that they're already independent, then we do the probability of A just times the probability of B. But again, that's only if we have independent events. If we don't have independent events, then we have to use the rule from earlier that has conditional probabilities involved. But when we're talking about a deck of cards, when we put it back, they would be independent. So that's a lot of time we talk about decks of cards here. We have determine whether the events are independent and justify, shuffle a standard deck of cards and turn over the top card, put it back, shuffle it back in. If A is getting a heart and the second card is a heart as well, these are independent since we replace the cards. Now, what if we shuffle a deck of cards, turn over the top two one at a time? That is not independent because depending on what the first card is, the probability of the second one can change. Knowing the suit of the first. Okay, and this last one, 28 students in Mr. Tabor's AP Statistics complete a brief survey. One of the questions asked whether each student was left or right-handed, and there's a two-way table that summarizes the data. The events of interest are female and right-handed. Going on to the question, I guess there is no question listed. The question is probability, whether they're independent. And so what we have to test is, remember, the probability of A has to be equal to the probability of A given B. So let's find the probability in our case here, female, whether that's the same thing as the probability of female given right-handed. So let's get all of our totals here. And a total of 28. So for the probability of being female, we have 21 over 28. And the probability of female given right, so that's where we use the 18, the intersection there, and divide by the total of the one that's given, which is 24. Oh, I said 28 and wrote 24. Since those are not the same, let's see if they are. Use our calculator here. This is 0.75. 18 over 24 is 0.75, so they are independent. You wouldn't think that they were looking at them, so that's why we have to do that calculation. Alrighty. Following the Space Shuttle Challenger disaster, it was determined that the failure of O-ring joints in the shuttle's booster rockets was to blame. Under cold conditions, it was estimated that the probability that an individual O-ring would properly function was 0.977. Assuming that O-ring joints succeed or fail independently, what's the probability that all 6 would function properly? So if we have 6 functioning properly, since they are independent, we can just do the probability of proper function times itself 6 times, which would be just knowing the probability they properly function to the 6th power. So in our case here, that would be the 0.977 to the 6th power, which is 0.87. So there's an 87% chance that the shuttle would launch safely, which doesn't seem very good. And last question of the lesson here, last page I should say. During World War II, the British found the probability that a bomber is lost in enemy action over occupied Europe was 5%. Assuming that missions are independent, find the probability that a bomber returns safely from 20 missions. So very similar. We take the probability of safe return, and since we want 20 of them, we can just raise it to the 20th power, knowing that they're independent. So 5% to the 20th power. Oh, sorry. The returning safely was the complement to the number they gave us, 1 minus 0.05. So that's the number we're raising to the 20th power. So 0.3585, 35.85% chance of returning safely from 20 missions. And government data shows that 8% of adults are full-time college students and 30% of adults are 55 or older. Because when we multiply them, we get 0.024. Can we conclude that 2.4% of adults are college students aged 55 or older? No, because being a college student and 55 or older are not independent. And that finishes up our section 3 on conditional probability and independence.